Real-time collaborative editing requires a system that can process immediate local keystrokes while simultaneously managing delayed network states from other users. To maintain a 60 frame per second UI render loop, you have a rigid budget of under 16 milliseconds per local execution. If the interface waits for a network round trip before displaying a character, the user perceives lag. This requirement makes traditional database locking impossible. Locking a document while one person writes ensures consistency, but it forces every other collaborator into a literal waiting line, killing the collaborative experience. On the other hand, optimistic replication, where you simply let everyone write and hope for the best, usually relies on last writer wins. For sequential text data, this is disastrous, as concurrent edits will silently overwrite each other. This leaves architects in a corner. Local edits must be applied instantly to keep the UI snappy, but that instant execution creates a risk of uncoordinated changes known as positional drift. Systems model text as character arrays mapped to numeric indices. If user B inserts at index 0, the array expands, shifting subsequent characters downstream. When user A's delayed delete targets index 1, the shifted indices cause it to destroy the wrong character. Resolving this corruption requires a choice. You either build an engine that rewrites operations in transit, or you abandon the numeric array structure entirely. The first strategy is operational transformation, or OT. This model treats numeric indices as unstable and prevents corruption by actively recalculating and rewriting operations as they arrive. Because these operations must be rewritten based on a strict historical timeline, OT requires a single source of truth. This forces a hub-and-spoke network topology. The central server acts as the authoritative sequencer. It compares incoming operations against its own history and calculates the necessary shifts to ensure the user's original intent is preserved before broadcasting the corrected command. To guarantee that every user eventually sees the same document, OT must satisfy transformation property 1, which ensures that concurrent operations reach the same state regardless of the merge path. The difficulty lies in transformation property 2. This requires that transformation paths commute seamlessly across 3 or more concurrent operations. In a decentralized network, every user receives updates in a different order. Reconciling every permutation of those edits without a central timer to keep them in order is essentially impossible to implement with errors. Because of that complexity, operational transformation is only reliable when you have a central server to enforce a master timeline. User intent is preserved, but only through centralized infrastructure. The decentralized alternative is conflict-free replicated data types, or CRDTs. This approach sidesteps the coordinate problem by abandoning relative numeric indexing entirely. A sequence CRDT ensures positional stability by assigning every single character its own globally unique and immutable identifier. Since these identifiers never change, operations naturally commute. Any user can work offline and merge their state back with others perfectly, because the coordinates for each character are permanent and independent. However, this permanence creates a new bottleneck. If you physically delete a character from the data structure, you break the logical pointer chains that other incoming edits might need for positioning.
Consequently, data in a CRDT can never be truly removed from the system's memory. This leads to the tombstone tax. Deletions merely flag a hidden Boolean attribute. The character disappears from the UI, but its metadata remains permanently locked into an ever-expanding structural graph. While CRDTs allow for perfect decentralized convergence, the trade-off is massive. A simple 10 kilobyte text file can balloon into a 100 megabyte graph that exhausts the memory of the client's browser. For complex text, these are the primary models, but for simpler data, like list ordering on a dashboard or object properties on a canvas, both OT and sequence CRDTs are often over-engineered. Instead, many teams use atomic operations. Here, mutations are limited to single property updates that resolve conflicts using a simple last writer wins rule. To handle ordered lists without numeric drift, these systems replace standard integers with fractional indexing. To insert an item between two others, the system calculates a midpoint. The new item is assigned a fractional value halfway between the existing coordinates, which requires 0 updates to the surrounding items. To prevent two users from calculating the exact same midpoint at the same time, the system appends a randomized string, or jitter, to the coordinate to ensure uniqueness. Combining atomic operations with fractional indexing allows engineering teams to support live collaboration while avoiding the architectural weight of traditional text editing algorithms. The choice of a collaboration engine dictates the limits of your entire system's network topology. This matrix clarifies the application for each model. Server-ordered OT is the standard for centralized enterprise suites. It preserves exact rich text intent while keeping the client's memory footprint low. CRDTs are the choice for offline-first or mobile applications. They function in unreliable network environments by exchanging high memory usage for the ability to sync states without a central authority. The hybrid strategy is built for visual editors and data dashboards. It relies on atomic properties to keep server logic simple and memory usage predictable. Every architecture forces a choice between sacrificing server CPU overhead, client memory capacity, or the granularity of the state itself. Distributed collaboration now faces a new pressure, the integration of superhuman AI agents. There is a massive mismatch in velocity here. While human typists reach about 80 words per minute, AI agents can emit continuous streams exceeding 4,000 words per minute. This volume can starve an OT system. The flood of writes saturates the central sequencer, creating a bottleneck that blocks human keystrokes and introduces severe lag for everyone else in the document. For CRDT systems, this speed triggers an explosion of metadata. Every character modification generated by the AI adds to the structural graph, causing the document's memory footprint to grow at a rate that can crash a user's browser in minutes. Surviving this throughput requires specific mitigations. Automated inputs must be batched into block-level changes and throttled through dedicated network lanes to protect the experience for human users. Data convergence relies on matching these algorithmic structures against the brutal execution constraints of a production environment.